Okay, so now let's see if we could figure out if these children are correct in their reasoning or not. The teacher asked them to express 154.25 in a different way, and each of them did try to express themselves in a different way. For Anita, she's saying it's 15 tens and 4 ones and 25 tenths. The number we're hoping it to become is 154.25. This is Anita. Now, when you give an assignment like this, you're asking the students to give you feedback, and the feedback they give you has little indicators in it of different reasoning that may or may not be appropriate. Like, for example, we have 15 tens, that sounds good. We have 4 ones, that sounds good. And then we have 25 tenths here. I want you to look closely at what this says right here. As a math teacher, with the children, when you see a child express himself this way, you have to make sure that that you correct them if they're saying that wrong. If they say it wrong and you say great job, then they'll think this is the way to do it every time. This is where we develop a worry about math anxiety and all that kind of stuff. But what does 25 tenths mean? Well, let's take a step back from this. You went to middle school and high school. You've learned what tenths means. What does 25 tenths means? It means 25 over 10. What is that? 2.5, right? So in other words, the child was trying to express 0.25. And what the child said was 2.5 ultimately when they said 25 tenths. If they said 25 hundredths or 25 pennies, that's different. But this is 25 tenths, which is ultimately 2.5, right? So this is what we mean by looking at the children's reasoning and making assertions about, are they thinking the right way? Is there anything I could kind of fine tune for them while I have them in my class, while their education is coming from us? Is there a way I can make sure they never make a mistake like that again and understand in a very good way what tenths are? You know, that's what our role is as instructors, try to do that. So look closely at what they say. Look closely at what the children are saying and see if you can help them in ways that you didn't think you could. For example, we have another student, her name is Becca. Becca is thinking about it this way. It's 150 ones and then 42.5 tenths. Okay? So is Becca right in her thinking? Well, let's see. 150 ones, I like that. 42.5 tenths, that's kind of a little bit funny. What do we mean by tenths? Well, again, what does the word tenth mean? Tenth means divide by 10. So let's see what happens when I take 42.5 and divide by 10. What do I get? If you can't see it in your mind's eye, get a calculator. But when you divide by 10, we should remember you just moved the decimal point 1 unit left. It's 4.25 is what that quantity is. When you say 42.5 tenths, the quantity looks like this. Now, does it make sense? 150 ones and 4.25 more. That does make our number that we're hoping for, 154.25. So we're going to say Becca's right. I'm going to say right now that the girl with the letter A is incorrect. I can't remember what it is. And the girl with the B is correct. Okay, so far so good. Anita was her name, sorry. Okay. The next one we're asking about is Cedric, who believes that it's 1542.5 tenths, in comparison with Dario, who thinks it's something else but in hundredths. Let's think about both of those and see if they're accurate or not. Remember that we're hoping for 154.25. Right? So we have Cedric C is saying 1542.5 tenths. Okay. And then we have for part D, Dario is saying 1.5425 hundredths. I forgot the N in there. Okay. All right. Let's check them and see if we can make heads or tails of this is fair. Okay. Well, is this number going to be the same quantity as that number? Let's see. This number is in tenths. I think we already established that tenths means over 10. We can also apply that here. Hundredths means over 100, right? So let's make this tenths now. Oh, wait a second. This says hundreds. Hold on, guys. Excuse me for a minute. I think I made a small mistake writing this down. Take a look again here. Notice that Dario is not saying hundredth. He's saying hundreds. Let me write that very clearly. Right? Hundreds. We have tenth and hundred there. So keep that in mind, okay? And that does make a significant difference. It's important to notice that. So let's look here. What does it mean, tenth? It means divide by 10. What does hundreds mean? It means times by 100. See, if it was hundredth, that would mean divide by 100. This is hundreds. That means multiply by 100, right? Okay. So here we'll take this and divide it by 10. You can either use a calculator or you could do this the old-fashioned way. Divide by 10 means move to the left one spot like that. Okay, looks good, Cedric. I would say this is just fine. This expression does ultimately give a quantity that is representing 154.25. Nice job. How about Dario? Well, Dario's in hundreds. So we're going to take this figure and multiply it by 100. You're multiplying by 100. That's the same as going 2 spots, remember? So I got 154.25. Again, nice job, Dario. Okay, so we could say that Cedric and Dario are on the right track. Their thinking process is appropriate, right? And then our last one. We have 154 ones and 0.25 hundredths. This is for part E. And for part E, we're saying 154 ones, and we have 0.25 hundredths. And again, it's got that TH in there, hundredth. So is this an appropriate expression of our number, 154.25? All right, well, I like 154 ones. Let's examine this 0.25 hundredths. Remember what that means. Hundredths means divided by 100. So it's 0.25 over 100. And the way we'll figure that out is we'll take this decimal place and we'll go 2 places to the left, which means I have to put zeros in there. So this is really the same as 0025. Means that this quantity is really 154.0025. No good. So we're sorry, student E, but this is not an appropriate way to express 154.25. This student, you might want to explain to this student that hundredths is not the same. You could have said 25 hundredths, not with a point, but instead just 25, and that would have been right, or something, but have a conversation with them so that they're okay with it and they understand the material that way, okay? Now, once again, I want to encourage you, if you have questions, to please go ahead and speak up and say what you're thinking. Remember, you have to unmute in order to contribute, okay? So now let's talk about bases other than 10 and why we would have bases other than 10. If you take a very close look at all of these beautiful characters from our childhood, you'll notice they all have something in common. And what they have in common, of course, is they all have 4 fingers on each hand, which is kind of a little bit weird, but you kind of almost never notice that Mickey Mouse has 4 fingers. Tom and Jerry have 4 fingers. The genie, even Aladdin, has 4 fingers. You'll notice also Bugs Bunny, Homer Simpson, SpongeBob, they all have 4 fingers. Why do they have 4 fingers? Well, there's a deeper reason to that. It has to do with art. It's a long story, and I encourage you to investigate it and explore that. But the reason why this is being brought up in class is because A, to the elementary students, when you put this up on the wall, everyone's going to feel happy. That's a good thing. It'll get everyone engaged and we'll all start thinking together. B, it'll make students think about the origination of numbers and why we count the way that we do up to 10. Because the reality is the reason why we count up to 10 is because we have 10 fingers. I mean, if you didn't have the luxury of an education and growing up in a good community and in a good society where we were advanced with our technology the way we are, but instead you had to find a way to make it and survive without all of that. You would be trying to count and remember things. How could you remember how many eggs your chicken laid? How can you remember how many cows you still have in the field? Things like that. How can you remember how many seeds you planted when you were farming? Well, you have 10 fingers on your hands, and we kind of think about tens. We kind of think about tens because it's the thing that we can use that's most immediate to us. And that's one of the main reasons why we use 10 as our base in our decimal system. And as you can see, the cartoons, they would be using a base 8. So we have a cute little segue into the idea of base 8. And you could start talking to your kids about, well, how would Tom and Jerry count? They wouldn't count to 10 and then count to 20. They would count to 8 and then they would count to 16 and stuff like that. And the fact that they have a different amount of fingers kind of opens up the kids' imaginations to make them be able to understand and grasp this idea of an alternative numeration system with a different base than 10. You could also do this with counting with something as elementary as apples, or you could use erasers, or you could use anything for this, any kind of counting tool. We have a group of apples, and it's a big pile of apples. And as you could see, we could count them the old-fashioned way with just pointing to one at a time and saying out loud the next number. We can group them in tens and ones also if we want to make it clear. For example, if I deliberately separate them so that I have a group of 10, it turns out that I wind up being able to make two groups of 10, as you can see there, and then there are 6 remaining. The way that we are separating these apples into these groups helps students see the idea of place value and represent that we have a 2 followed by a 6 if we write them on the bottom the way that looks, okay? Also, we could say, well, if you're going to group them in groups of 10, like you're counting like a human being with 10 fingers, well, imagine that you're the genie and you have 8 fingers. How would you group these apples? And so now you can see we have 3 8s and we have 2 1s. In base 8, it happens to be the case that 3 2 is the way you would say the number 26. And notice that I'm saying 26 because numbers like 20 and 30 and 50, those numbers come from the idea of a base 10 language. In base 8, we don't have those numbers. All that we have in base 8 are digits, and we only have 0 through 7 as our digits. So the way we recite numbers out loud, we would not call that 32. We would call that 3 2 base 8. And we're going to talk about how you can express that and how you can write that also in the next coming lessons. But this is another amazing example illustrating for the tactile learner how to move objects around to grasp the idea of a numeration system other than 10. So while we're in the conversation, why don't we explore what it looks like to be in base 3? And here we're talking about the idea of grouping things in terms of groups associated with digits in base 3. First, let's ask the question, what are the digits of base 3? And this is kind of an important thing that we need to discuss and get familiar with before we start playing around with this example. The base 3 numbers, in base 3, you will have 3 and only 3 digits. Let's reason why. In base 10, there are 10 digits. They start with 0, and they go up as far as they can so that there are a total of 10. Notice that 10 is not a digit. The digits go from 0 to 9, and in base 10, the number 10 is not a digit. That's a general conjecture that you can always rely on. For example, in base 3, the number 3 is not a digit. There are 3 digits, and those 3 digits are 0, 1, and 2 only. Okay? If I want to express 3, I have to take the next digit and put a 0 next to it. The same way I had to take 1 and put a 0 next to it to express 10 in this base. For one last example, what about base 8, which is octal? Base 8 has 8 digits, and those digits happen to be 0 through 7. And in our last example, we proved that the number 26 is equal to the number, oh, what was it? I forgot what it was. Three, 2 in base 8. Okay, so we've got some interesting little insights here. Got a couple of different examples here, and I hope that you'll remember this, because now when you try to experiment with moving around in different bases, you know, we need to remember these little facts. Okay, now let's return to our lesson where we were talking about base 3, and notice in base 3 we're going to rely on the fact that 0, 1, and 2 are the only digits, and there are 3 and only 3 digits in that base. This table is trying to show our students how to count in those bases. For example, we have in base 10, we have no blocks means 0, we have 1 block means 1, we have 2 blocks means 2, and we have 3 blocks means 3. But if we were in base 3, what would happen is we would be able to express 0. We could just write 0 base 3, as you see right here. We would be able to be expressing 1, we would write 1 base 3, and we'd be able to express 2, so we write 2 base 3. But notice that we can't express 3 by writing the number 3 here, or writing the Hindu Arabic numeral 3 here, because 3 is not one of the appropriate digits in base 3. We've just explained and discussed how 0, 1, and 2 are only. So how can I express this? Well, if I wanted to try to represent the idea of 3, it would be actually that I have one group of the next power up and then none of the ones. In other words, take a look right here, guys. For 3 blocks, it's going to be 1, 0, kind of like a number 10. It looks kind of like the number 10. Why? The reason why is because there are 0 ones and there is 1 3. And remember the way to read this number, and I'm going to do that in large print on the side for you. If you want to say this, what you're trying to say is you have 0 times 3 to the O, and then you have 1 times 3 to the 3. Doesn't that give you 3? Oh, wait, 3 to the 1. Sorry, what did I put there with 3? 1, you know what I mean, guys. The 1, excuse me, right? This is the 1's place. This is the 3's place. If we were in decimal, this is the 1's place, this is the 10's place. But we're not in decimal, we're in 3. This is the 1's place, this is the 3's place. So if we do the arithmetic, doesn't it make sense that we get 3 as our solution for this? By adding up 0 plus 3, we get 3. And in other words, there's a new conjecture that we can always write 1, 0 to say the base. So 1, 0, it's like I lost some ink there. 1, 0 and base 4 is 4. 1, 0 and base 7 is going to be 7. 1, 0 and base 33, guess what it's going to be? 33. All right? And what we're trying to say is that we mean that there are no ones, and there's one example of the base to the power 1. And so 103 is going to be representing the number 3. All right? And now the next number up is going to be 1, 1. So think of it like this, guys, and let's do a little bit of a table so that it's very clear, okay? In base 10 and base 3, and let's examine what the numbers look like. In base 10, the number 0 is 0. In base 10, the number 1 is 1 in base 3. The number 2 is 2 in base 3. But then in this one, and let's come out of here so that you could see it, to try to figure out now what 3 would be, we'd have to start fresh because we've used up all our digits. So I'll start fresh, 0, and I'll bump this up 1. Get it? To get 4, I'll bump this up another 1. To get 5, I'll bump this up another 1. But now to get 6, I've exhausted them all. So I have to go back to 0. And now I could bump this up to the 2. Let's keep on going. If I was trying to get 7, it would be 21. If I was trying to get 8, it would be looking like 22, but it's not, it's 2, 2. And then if I want to get 9, it's going to be 2, 3. But then what would 10 be? This would have to return to, oh wait, this would have to be a 0. Hold on, guys, I'm giving it to you wrong. I'm so sorry. There is no 3. We have to use a 0 there. So this becomes 3L, right? My bad, I'm sorry. I'm not trying to confuse you. Sorry about that. Not 100. That's the second time I screwed up. Guys, have patience with me. I'm sorry. The answer is 100 that goes here, right? My bad, my bad. Sorry about that. The reason why is because, and let's talk about what happened there. When you were at this position, right, where you had 8 and you had 22, this has to bump up to 0. So this has to bump up, but it bumped up to 0, so we get the 1 for the 9. Okay, it's 100. To get 10, now you're at 101. And 11 is 102. And 12, now we go 110. And see, what happens is all of these numbers, none of them uses a 3. And when I got to here, I got a little bit tired, and I started messing up. Remember, you can't use 3. And maybe my human error there will kind of make it clear for you if you follow through the lesson. And I'm not trying to mislead you. I'm so sorry about that, guys. But yeah, here, at first I made the mistake of putting a 3, make some little mistakes. But just remember, you can only use 2s and 1s and 0s in every number if you're in base space. So I hope that helps a little bit, trying to make that really clear for us. Okay? You might want to look at these as groupings. Also, you'll see that they put the 3 connected blocks there, and now there's one more there. You can look at it that way too, if that makes sense, if it helps. Okay. All right. So what we're going to do now, guys, is we're going to end our lesson here. I'm going to come back to say hello one more time. And to say I do genuinely appreciate your close attention to our lesson. And I hope that that was really clear and helpful for you. Bases are really not that challenging. They just kind of require a little bit of a closer attention. Your textbook goes into depth about using fractions and negative exponents with bases. We're going to not do anything with that stuff. In structures, I'm only going to have you doing positive exponents for your place value practice. I've deliberately eliminated all of the questions out of WebAssign that have negative exponents in them. So when you read through the chapter and outline it and get familiar with the material, please read through that part, but know that it's not part of our requirements for this course. And if you are confused about it and you feel like you'd like to talk about it, I'm happy to discuss it with you. But just know that it's not going to be taught and it's not part of our instruction or assessment. We're only going to be doing what you see here and going back and forth with bases, but only with positive exponents and positive place values. We're not going to study tenths, hundredths, and thousandths in the realm of base 3 and base 8 and so on. Okay? I'm going to take attendance before we dismiss. And then after we dismiss, if anyone has any last minute questions or quick ideas, I'll still stick around after class to address those ideas. Okay, so everybody please sit tight. We're going to stop our recording now, and I'm going to take attendance. Thank you so much for your attention, everyone.